All right, well, thank you very much. Welcome to the second half of Lydia's tutorial, and, well, may as well get started. Lydia?
Okay, welcome back. Yeah. So just to recap what we've done. In the first part of the first part, which I thought would be just the first part, we talked about information and work, and how these two concepts are related. And then in the second part of the first part, we started talking about treating thermodynamics as a resource theory. And I introduced this framework of thermal operations, where we allow for unitaries that conserve energy and entropy, and we allow for thermal states as modeled by Gibbs states to be connected to my system. Okay? And then we talked a little bit about why this assumption of thermal states is partially justified. And we saw that there are still some open questions, and there's still some open questions about why we allow for unitaries at all. Okay? So we have this model, which is a very simple kind of toy model, and we're going to see what we can do with it. So first, let's look at a simple example, which is when the Hamiltonian is degenerate. Okay? So then what you get, you allowed all the unitary operations, and you're allowed Gibbs states, but Gibbs states on a degenerate Hamiltonian just mean a fully mixed state. Okay? So this is the framework of noisy operations. You allowed mixed ancillas, and you allowed unitary operations. So if you have this, the order that you get in your states, in your resources, is majorization. Okay? And so first, just the formula here, and then we'll see how to visualize it. So this just means that if you order the eigenvalues of the states, then starting from the biggest eigenvalue, one state, the sum on one side is always bigger than the sum on the other side. So this is for all k. So what this means here essentially is that rho is more pure than sigma. And we'll look into this in a moment. There's a very nice review of this framework by Gore and Nicole and Rob Speckens and some other people. So what you get if you have this kind of pre-order on your set of resources, then your monotones are all the Schur convex functions. So in particular, you have this thing here, which is a divergence or the Renyi divergence to the set of free states. So some of you are very familiar with this, and I will not say anything new. For the others, this is almost like an asymmetric kind of distance measure. Okay? It's not a distance because it's asymmetric, but acts like this. So it's a monotone that is operations, and the closer the more similar that rho is to the state on the right, then the smaller this is, or the bigger. Okay, and the classical formulation is like this, and then there's several quantum generalizations. They all have different properties. They're all useful for different things, and as we'll see, well, in this case it doesn't matter because since all unitaries are allowed, you can always diagonalize every state. So therefore, you're like essentially back in the classical case. Okay, and later on it will matter, but we'll not go in much detail about this. So you can use these guys to define entropies, and therefore all the entropies are also monotones under this, okay? Which makes sense. So how do you visualize this pre-order? One very popular tool is to build the so-called Lorenz curves. So let's see what this means. So first you have your state, and you know how normally you can represent probability distributions like this kind of bar graph, okay, where here's like the probability of the first outcome and of the second and third and third. For example, for the state that is green, and this state would be a maximally mixed state. Yes, this would be the next. Okay, so you just sort your eigenvalues, and then you build a step function from this, which looks like this. So here we have 3 different states. And then you integrate this steps function. Okay? And you get the Lorenz curve. So straight lines corresponds to the to the maximally mixed state. Yes. And all the others are kind of above the straight line. And now how do you visualize your pre-order here? So it's very simple. If one curve is completely above the other, then it can be transformed. Then you can do this transformation, right? So for example, you can transform the green state into this maximally mixed state, yes, into the orange state, yeah, because it's completely above each other. Yes, so this condition corresponds to this condition here. Yeah. But for example, you cannot transform this green into the blue, nor can you transform the blue into the green in a simple case. Yes? Okay. And then you can say, okay, so this is, in this simple example, you get entropies as monotones, you get this very nice pre-order. Let's see what happens if now you allow for full Hamiltonians. And actually, in this case, I don't want to say that little is known, but there's still a lot to explore. So for example, we have a pre-order for block diagonal states. So these are states that are block diagonal in the energy eigenbasis. So we could almost call them classical states. Yes? So you don't have coherences between different levels, different energy levels. And in this case, it will be the pre-order that you get is thermal majorization, which is kind of a rescale majorization. We'll go into this in a bit. The monotones, again, not surprisingly, the relative entropy to the thermal state is a monotone. So in general, there's a nice result by Gao and Brandão. If you have some kind of a measure that behaves more or less like a distance, and you compute it towards the Gibbs, towards the free states, then this will always be a monotone in your resource theory under some assumptions. Yes? And then you're going to get these rescale Lorenz curves. And if you want nice reviews on them, there's this paper by Lorenz and also by Hordesky and Oppenheim. So how do you build now these Lorenz curves? So the idea is that before, the only thing that mattered was the probabilities. They needed to be ordered. So more pure states are better. But now you kind of have to weigh this with the energies. So the way to do it is you first need to rescale your eigenvalues, multiply them by the kind of the energy of your state, yes, like this, and sort them, again, from bigger to smaller. Then you build your step function again, where this things here just means that you kind of stretch this x-axis such that in the end, the function has this kind of boundaries of like being, it will be like from 1 here and all the way up 1 here, okay? This is just so that it's easier to compare systems of different sizes, for example, or states of different systems. Yes, so you build this, you rescale them, you build a step function, you integrate, you get a Lorenz curve, which is just like the other one. Yes, and then you have, again, a nice visualization, and I think, I don't know if Jonathan will talk about this in his talk, or Carlo, go into more detail, but if you read any papers about thermal operations, you'll see this Lorenz curves all the time, okay? And then again, the pre-order is the same, so it just tells you that if one curve is always above the other, then you can do the transformation. So, yes. So, I'll talk about what is the sufficient condition, what's the necessary condition. So, one thing that you get from here, so this pre-order, as I said, is only completely defined on block diagonal states. Okay. So then, but what you get from this is that you get that the free energies are monotones for all states, including coherent states. Yes. And what are these free energies? So essentially, they are a rescaled divergence. So you take this thing that you knew was a monotone, and then you multiply it by KT, okay, and then you take away this log z, which is a constant that depends only on your Hamiltonian. So why? I mean, we had such a nice monotone. Why are we transforming it into this? It seems like there's no added value, and the added value is just to relate this to the normal thermodynamics. Okay. So for classic states, this is also a necessary condition. So in particular, if the alpha that you use here is 1, then what you get is a trace of it's kind of the average energy of your state minus kT, the entropy of the state. And this is the free energy in traditional thermodynamics. So what we've done here was to simply, to start with this very almost naive model of just saying, well, we'll only allow for unitaries that preserve energy, and then we allow for the Gibbs states to come for free, and then see that we're already recovering a thermodynamic law and quantities that we had in thermodynamics. Plus, now that we have a quantum state and we have lots of states out of equilibrium, we get a whole family of them. Okay, as you can change this parameter alpha here, and you get a whole family of monotones that for classical states are also form sufficient conditions, necessary conditions, yes. And this rescaling in particular, what it does is that if you evaluate this on a pure state of a certain energy, then it gives you just this energy, okay? So what the free energy tries to encode is kind of the work value of your state, because it means that you could transform it to like a weight that you lift exactly to E. Yes? Okay. So this is kind of the hopefully very convincing application of this framework, telling you that, well, we do get something useful out of it. So there's also many rederivations of the third law that you can get from here by using other monotones, which tell you, so what the third law tells you is that you cannot cool something to the ground state if you only have finite resources. You need either infinite time or an infinite path or variations over this. Okay, so there's different results that recover this. We already saw Landauer's principle being like the work cost of erasing a system in the presence of a memory. And we saw this result is kind of for the average case if you have many copies. But there's also single-shot results that use where you can have like a probability of error, that things can go wrong with some small probability. You have some tolerance. And then the entropies that come up obviously are not then the von Neumann entropy, but some other single-shot entropies, okay? So what this is very nice for is to give a physical interpretation to your information theoretical entropies. And clearly, if you have some finite size effects, like your bath is finite, then this limits the efficiency of your procedure. Because if you remember the protocol to do this erasure, it assumed that you had access to like a heat bath that was as big as I wanted, where I could draw whatever qubits I wanted. And now if you want to study more realistic situations where this is not the case, then you get all these finite size effects. Okay. Now, something that I will not talk about much because Jonathan will go into more detail later in the week, are fluctuation theorems, which what they tell you is, well, these results are kind of average results. So what is the probability of things go wrong? Or how badly can things go wrong? And what they tell you is that this probability is exponentially suppressed on the kind of variation that you'd get. Yes? And this is it sounds like, how would you even quantify this violation of the entropy, so of the expected energy that you can extract from a process or not? So one thing that you could do is just, well, measure my energy reservoir in the beginning, measure it at the end, and then use this as the work extracted. But of course, that if you have a coherent process, then you'll end up also with a coherent state in your reservoir, and then you have to be much more careful about how you model all of this. So like in the same way that you had to be more careful when you had a quantum memory, you could not just read it. Now, here in this case, you also have to treat these things with more care. Okay. So the other thing that you can do is, well, we have this framework where we have only one conserved quantity, which is the energy. Okay, we only care about energy. And now we say, well, maybe in real life, there's also other laws like momentum conservation or some other quantity that needs to be preserved. And then let's see, well, let's just expand the framework. And what we say now is, okay, so now we have these other observables, and our unitary also needs to commute with them, so it cannot add any momentum or cannot add any of these other things. So what do we get from here? Well, we get essentially most of the same results, but now for a different kind of Gibbs state, a generalized Gibbs state, okay, where you just have you have kind of a different effective temperature for each of these observables. And again, all this typicality thermalization results apply. So in particular, the static thermalization results. So if you take a maximal mixed state on the big system, then locally it appears to be like this. Yes. Also, the passivity results also hold here. And the monotones you get, not surprisingly, you get, again, this fake distance, this divergence to the generalized Gibbs state. And we're starting to see the first protocols to try to convert between all of these quantities. So for example, you could have one reservoir that only stores energy and one reservoir that only stores spin, but has a degenerate Hamiltonian, and you want to trade between these two quantities. Okay? And here there are very interesting effects when these quantities do not commute, and this is a nice area to explore. Okay. But so far, most of this could have been almost a classical framework. So when do we start to see like real quantum examples or quantum phenomena? We can start by looking at coherence. So the first thing is that we could be interested in implementing rotations in your state, like we saw before, like going from 0 to plus, etc., that are coherent. But in general, how do you implement a unitary on the lab? You shoot a laser at some system, okay? And this laser is a very big coherent system. And you can say, well, actually, I want to account for this resource that I'm using. And can I optimize this resource? So one of the first results on this topic was quite surprising, which was that this coherence is in a way catalytic. Okay? So what does this mean? Well, so suppose that I model my source of coherence as say, harmonic oscillator, right? If it's a laser, then it's a very large coherent state on this harmonic oscillator. So what are the properties of this that are important in order to implement unitaries? Okay. So the properties turn out to be just two aspects of this. So one, this M is easy to understand. It's like the lowest occupied energy level of my, say, harmonic oscillator. And the other one measures how well spread this coherence is. Okay, it's this term here. And what I mean by these are the relevant properties, it means that if I want to implement some unitary to some precision epsilon in some system, then the only things that matter are these. Okay, so then you can see, well, I implement a unitary, and then what happens to my coherence reservoir? And this is the idea. So there is some back action, of course, of implementing an operation. Yes? So my reservoir is changed. And in particular, the state gets kind of more stretched. But it does not degrade this relevant parameter here, this delta. Because it stretches, of course, it lowers this M, which in the end, it just means that, the M is not really important. It just means that at some point, if you keep stretching it, you're going to hit the bottom. Yes, and once you hit the bottom, then at some point, it starts affecting your total coherence. So what can you do? Well, I can just pump this up with energy. Yes, I just add energy to this system. So this is interesting because it sounds like you can trade. If you start with some initial coherence, then you can just add energy and keep this coherence for all practical purposes that you're interested in. Yes. So in that sense, is what we say that it acts as a catalyst. Anyway, this is in the very specific case of this, of taking a harmonic oscillator that is actually unbounded in both directions. Then you can start looking at more realistic reservoirs. And so, for example, there's this paper by Imperial people, I think, in which they give you an explicit protocol to extract work from coherent states, to implement unitaries in coherent states, and then later to restore the reservoir. Yes? Okay. There's also quite some work now from 2 years ago on resource theories of coherence that just try to study the system, and then resource theories that try to study coherence together with thermodynamics. So this is also an interesting direction to explore. Now, finally, to go back to the question I was asked before the break. I mean, the elephant in the framework is that we allowed for all this unitaries to be applied, but of course that if you apply unitary, this means that you choose a Hamiltonian, you turn it on at some point, and then you turn it off, right? And in order to do this, or your Hamiltonian could even be something that is time dependent, okay? In order to do this, you need to have like an explicit clock system, okay, that keeps track of everything. So for example, in ion traps, they sometimes use extra ions that act as clocks themselves. Okay, so then we really want to have like, if thermodynamics is about accounting, then we want to account also for these resources. So we need to expand our framework to think about giving agents less control. Just say, well, you can turn on some interaction, then you can turn it off later, but with not very good time precision, so that you're forced to model this explicitly. Okay. So what are first steps? So there's this idea of having an ideal clock that is just a particle in a line, perfectly coherent. And in this case, well, it's catalytic. You can use it as many times as you want. And it also allows you to implement your unitaries perfectly. There are some results now in which you modify your framework such that you don't allow for unitaries, but you only allow for thermal contact, thermalization. And now more recently, and there will be a paper about this by Misha, I think. There's some explicit models for some clocks, which are finite-size systems, and then they study like how good this implementation is depending on the dimension of the clock and how much the clock is degraded. But again, this is a very interesting area for research, for directions. Okay, and yes? No, there isn't. In a sense that clocks are coherence. Clocks need this coherence, as far as you know. Yes. Yes.
The previous slide you were calling it coherence reservoir, and we can also call it just a clock, right? There's no difference.
They both use coherence. Maybe for one of them you want, you want it for a specific application, then you build them differently. But yes, I mean, you could call them the same, yes. Yeah. I'd say, yes, you have a different question?
So, and you said, the previous slide about coherence reservoir, you said this doesn't degrade. But
the state is degraded, but the parameters of interest do not.
But the next time you use the clock, the error you make will be correlated with the error you made in the first time.
Sure. These results assume that now you apply this clock to a different system. So in this sense, then it would not. If you keep applying to the same system, yes. Otherwise, no, it's good. It's good. It stretches the talk. So, okay. So the idea is, if you use the clock on a system, and then you're gonna use it on a different system, that's okay. Okay. Then these parameters are not changed. Of course, if you want to use the same clock in the same system, then this is a problem. Yes, because then the errors are correlated. Yes. And this, I think, correct me if I'm wrong, but I don't think it has been very much explored. Okay. So there's one thing that I haven't told before I go to open questions in this whole talk, and I didn't know very well where to put it to fit the story, which are heat engines and small heat engines. Okay, so I decided to put them here because heat engines are an example of autonomous thermal machines or thermal protocols, where precisely you just turn on some interaction and you forget about it, and you don't need any explicit control later on. So the idea behind thermal engines is to explore two resources that are very common. So in this case, two heat baths of different temperature. Okay? So it's like you can take one to be your environment and take the other one to be an extra resource that you have, but you just make it very big. Yes. And then you want to use this to do something. So in this case here, it could be you want to use it to cool some additional system that is also in a Gibbs state, or you could want to use it to extract work. Yes, so like take here to be a harmonic oscillator, and you wanted to pump this up. So, and the question was, well, how big does this engine need to be? Can we do it with only, just say, imagine having only here 3 qubits? Do we still get very efficient engines or not? And the result is that, yes, you can get Carnot efficiency, but let's be a bit careful about what this means. So the idea behind these engines is you take 1 qubit and you put each qubit in contact with a bath, okay, so that it thermalizes it. But you choose these gaps very carefully, such that they match in some way that is convenient for an engine. So in this case, like this gap plus this gap equals that gap. Okay? So then you can turn on some interaction. And in fact, in this case, there are some results that say most interactions will do, which is energy conserving. So for example, in this case, it could mean that, let's see if I get this right. Could mean that when this one goes down, exactly, and this one goes down, then this one goes up. Or you can change, yes, exactly, right? Because down, down, up, yes. And vice versa. If this one goes up and this one goes up, then that one goes down. Yes? And then you do this in a way because you know that here you'll always get, this state is always getting thermalized, so you always get a Gibbs distribution here, you always get Gibbs distribution here. And you fine-tune these probabilities, like by fine-tuning the gap, you fine-tune the probabilities that you get, such that in the end, the result on this state that is not getting thermalized all the time, for example, could be that, well, I'm always cooling down the system here, or the opposite, I'm always pumping the system up. Yeah? And you can do this by just letting it run. And it reaches Carnot efficiency, which is the maximum efficiency in the classical, like, macroscopic case. Now, what is the catch? Well, you need to fine-tune these gaps very carefully. You need to make sure that they actually thermalize, so there is some gap, some qubit in your bath that has the same gap here, so that these things actually thermalize. Yes? So in the end, you kind of still have some assumptions that you have infinitely large baths, yes? But they're just a bit more in a different layer. Okay. Good, so this is actually something that would be very cool for applications. Because if you have such a thing, then you could put it inside a quantum computer, for example, and have this computer self-cooling all the time. Okay, so now, for more, by the way, for more results on this, several papers by Paul Skrzypczak, and there's also a few reviews that I'll talk about at the end. Yes. Okay. So now let's talk about open questions. So first, my favorite area would be this clocks and control. I think it's where there's more room for exploration now, and also we get more useful and interesting results. So one thing that we need to work out is what are the most efficient clocks? Like, what is even like the best protocol for this? Both from the point of view of theory, but also from looking at specific experiment setups. So the second thing that we can do, and it's been done, is to combine all this thermal operations framework with insights from reference frame frameworks, reference frame resource theories, okay, because your clock is like a reference. Then apply further restrictions, like, for example, it could be that you cannot have this fine-tuning of paths of Hamiltonians in some experiment. So what we have to do is go to experimentalists and ask them, is this a reasonable assumption to have? And then try to build a framework for this. Then there's not yet a clean framework to treat this question of clocks. There's not, at least I haven't seen like a clean kind of resource theory formulation of how much control you give to an agent, how you quantify this. So that would be something small and simple to do. Again, seeing how much we need coherence, how much coherence is involved in this. And finally, since we're talking about clocks, then you can relate this to more foundational problems like the problem of time in quantum theory. Okay. So the other thing is try to make this whole thing more realistic. So try to make it less of a spherical cow, more like a real cow, free in the field. So one idea is to have more operational notions of temperature. So instead of modeling the bath via this Gibbs state, which is kind of a statistical approach, which we know already that it's not true. It's not a Gibbs state. It's like typically close to a Gibbs state, but it's not a Gibbs state. Okay? So we can either try to model this kind of knowledge of with high probabilities close to a Gibbs state, or we can go from a more operational approach. So for example, the way temperature is defined by Carnot, and there's a very nice overview of this in Feynman's lecture notes. It's just saying, okay, I don't know what temperature is, but I know there's some things called this heat baths, and I know there's one parameter that matters for the purpose of work extraction. Okay? So then by seeing kind of okay, then let's suppose that I have something called reversible engines, okay, that I can run in one way and then the other, and the work out one way is the same as the work in the other way. Okay? Just this idea. So I start from the work engine, the heat engine, which is something I can actually measure, right? How much work comes out, how much work comes in. And then I see, okay, so now let's try to compose these heat engines. Let's say, I have a bath that I'm just going to call it the reference. I'm just going to say this parameter is equals 1, call it the temperature, and see how much work I can extract from here to another bath, okay? And have this define the temperature of this other bath. So there's a whole argument that runs like this, and that later also results in all the laws of thermodynamics. But the idea that I'm trying to express here is that you don't start from this notion of temperature, you just start from something operational, like this work that you can measure, okay? And from here, you get some parameterization of your bath, like in this case, the temperature. So we could try to do the same for engines that we know work in the quantum regime, and then say, I'm plugging in a heat bath, maybe do this in an experiment. I think it's at a certain temperature, but let's see how much work I can get out of this, and let's see if I can parameterize this by a single parameter, which probably is not going to be the case. Now, there's been lots of work in finite size effects. There's been some work in going beyond like this idea that the bath is in a tensor product with my system, and going beyond the weak coupling also to derive all these thermalization typicality results. Okay, so this is something that is active. The other thing is having some realistic descriptions of resources for experimentalists, because maybe the experimentalist doesn't know that his system is in some quantum state rho that described by density matrix, but they've done some tomography and they know some confidence region around this. Okay? Or they know some some other parameters, some observable, and I want to know still, how much work can I extract from such a resource that I can only describe in this way. So in the same way that the original developers of thermodynamics did. Okay, you didn't know the exact state of your system. You just have some things called pressure and volume, which is the accessible information. And now we still have this. I mean, in quantum information, we like to think that not that we have access to the density matrix, but in fact, we still have some effective description. And so the question is then what kind of effective descriptions do experimentalists give us, and what can we do with them? Yeah. Okay. Yes, and also, in all this work, we cared a lot about heat and work, but it could be that, experimentalists tell you, look, we have a great way to cool our systems. Heat is not a problem. We have access to infinite energy. Work is not a problem. Actually, what we care about is coherence, or what we care about is, coherence times. And these are the relevant resources, and we should be building resource theories that take these things as the relevant things and try to study them. Okay, so the general message of this section of open questions is go talk to experimentalists and ask them what is important for them, and then build your models from there, not the other way around. Because otherwise what we have is that we see lots of experiments in quantum thermodynamics, and some of them seem a bit contrived that, we're measuring work in this way, and why in this way? Because it fits your theoretical model. Yes, but it's not like a work that you could later use for something else. It's not very operational or meaningful in that way. Yes? So we need to flip this the other way around. Okay. So the other thing is that since we saw that thermodynamics is so general, and it's just a resource theory, and we applied it to macroscopic systems, and we applied it to quantum systems, then we can try to apply it to other kind of ontologies. So we can take, for example, there's been some work on this, like on applying it to generalized probability theories. And it's still very baby steps, what's been done here. And we can try to see, like, what kind of GPTs get thermodynamic laws that resemble our world or not? And could this be a parameter to try to restrict and to rederive quantum theory, like it's done now with locality and correlations? So the other thing that one can do is then, if you have this, if you write an axiomatic thermodynamic in different physical theories, then you can try to relate them and try to see when they're similar, when they're not. And finally, there's the whole ADS-CFT field, which uses thermodynamics, but some of the notions used there can be seen as a bit naive. For example, the notions of thermalization used, or the fact that thermal states are already represented by the Gibbs state, or these kind of things. We can take some of kind of the operational insight that you gain from this framework and try to apply it to other fields of research. Yes. Also, like the insight that information is subjective and thermalization is subjective, and you always need to model your agent explicitly, could be useful. Yeah. Okay. With this, I am reaching the end. So there's a few reviews, of which here I'm only repeating the 3 that I mentioned during the talk, but there's a few others. So this talk's explicitly just about quantum information applied to different areas of thermodynamics. This one, here we are it's a bit, a bit like me. This talk is a very broad overview, more to give you intuitions, and not so much going into mathematical details. So if you want a mathematical detail of a specific part, then in this case, in this paper, they flesh out like noisy operations really, really well. Okay, and you can see like how these Lorenz curves come from and how you get all these monotones, et cetera, et cetera. Okay, so if you then later would like to start your own resource theory, thinking, oh, let's add this other assumption, or let's take this one out, then I would definitely recommend reading this before to see how one proceeds once you have this operational principles set. And finally, I didn't say much about thermalization results, and this is a very nice review of the field. Yes. Okay. Now, this QIP has a wealth of thermodynamic presentations and posters. These are just the ones I saw, and there's probably more. So I encourage you to go to all these talks. So in particular, Carlo will talk about resource theory where you have these two resources of heat and work, so you don't give the Gibbs state for free a priori, but you count it also as an explicit resource. And you'll explore this, so it would be a very nice follow-up to this talk. Jonathan will talk about many things, including fluctuation theorems in more detail than I talked to you. Okay. Yes, and there's also all these posters that you should go to. And that's it. Thank you very much for your attention.
So questions?
Yes.
So this way of measuring coherence, it somehow involves the choice of a phase, right? So somehow this operator that you showed, delta plus delta adjoint, it measures the real part of the coherence. Does this matter somehow? So
we got this measure because it's the measure that matters, right? We thought, okay, we have this purpose, which is implementing a unitary, and then let's see what's the measure that turns out to be relevant. And it turns out to be the real phase. You're asking me. Yes. Okay, I know that the question is different.
Rephrase the question.
Yes.
Would I times delta minus delta dagger be as good?
I don't know. But there are people in the room who do. Looking at you? No? Yes? No. Never mind.
Yes, the translation operator, so you want to treat the translation.
Yes. I mean.
Further questions?
The resource theory that you define here, it can also be defined in a pure classical settings. For example, you can imagine a probability distribution over a phase space that is, and you couple your system to a thermal state exactly in the same way. I was wondering if there is any fundamental difference between this quantum problem and classical problem that is defined only on phase space. And I guess the second part of the question is that what you call quantum thermodynamics or coherence, the effect of coherence in quantum thermodynamics, isn't it very similar to just having non-equilibrium probability distributions in classical setting? Let's say I can have stationary distributions and non-stationary distributions. So when you think about non-stationary distributions, there are some extra constraint on the possible transformation that you can make from one state to another. That is just due to the time dependence of this. So for example, if the first one is time independent, the second one, the final state cannot be time dependent. So is it really different, the type of constraint that you get in quantum thermodynamics? Is it different from what you get in exactly classical setting?
You know, this depends on what you mean by different. I mean, you kind of saying, I add one more constraint, and then I get one more resource that is important, and in that sense, it's very similar.
I'm basically asking if
I mean,
you need pure quantum effect here, because I can define everything here in also classical setting. And I mean, in what you presented, I didn't see any big difference in that classical problem and the quantum problem.
Yeah. I guess I guess the problem is that you want to implement this quantum transition, right? You want to treat this quantum problem of like, I want to prepare this state that is coherent. So in that sense, it's a new problem that you want to treat. But it's solved with this, okay, maybe lying, but I think it's solved with the same kind of reference frame kind of approach that the classical one would be solved.
Basically,
But
there is a classical resource theory of thermodynamics, and I
yes,
don't know if there is anything new in quantum resource theory of thermodynamics.
just the fact that it now allows you to treat states that you couldn't treat before, right? This is the main thing for me.
The free energy that we define here, for example, can be defined exactly in the same way.
Yes. I mean, this is, and it's only, and, you know, it's only like a complete family of monotones for classical states as well. Yes. There might be more generally quantum aspects, but we have not explored them so much yet. But the main thing is that now we can treat all these quantum transitions as well, I would say.
Any?
I mean, okay.
So just
Look,
to clarify,
yeah.
when I say classical, I just don't mean necessarily diagonal in the basis. I just mean
Yes, I know. I know what you mean.
when I
Yes.
think about the harmonic, classical harmonic oscillator.
Yes. Yeah. And some other things that, for example, the results on thermalization and on typicality of thermalization are much easier to achieve because you have a quantum space, which is a larger space, so you get this typicality much more easily. Which maybe you could not justify your assumptions as well if you had a completely classical theory. But are they really quantum things? Well, you can, you know, extract work from quantum correlations. You can't do this in a classical theory, but yeah.
Any further questions? All right. Well, if not, actually, I've got one.
Yes.
So lately, I've stumbled upon a little bit of controversy about the Landauer limit. I was wondering if you could comment about whether you've looked at any of these critiques that have come out within the last few years about it, or whether you just haven't looked at it.
Do you want to tell me any specific?
Oh, there's
critique?
like Norton and some other people came up with some critical claims that the Landauer limit perhaps hadn't been proved in exactly the ways that they would like to see it proved. And I was just wondering if you've looked at that, because I haven't.
Not in big detail. So what I've seen is like rebuttals of things saying, well, I mean, Landauer's principle is a principle, right? In order to prove it, you need to come up with a framework. And then you need to say, well, these assumptions are reasonable. Okay, so now here we have a framework that is, you can question all of these assumptions separately and then see if they're reasonable or not. Within this framework, it has been more than proved. You have finite-size corrections. You have now this new paper by equal people from December say about what happens if your heat path is not perfectly independent of the system you want to erase, and you get some corrections there as well, etc. Yes. So now, I mean, if you're talking about an objection of this type, then we'd have to discuss like what assumptions they would like to have, and yes. If someone knows, then I'm happy to discuss the assumptions.
If there's no other questions, let's again thank Lydia for an excellent tutorial.